This is section 3.1, exponential functions and their graphs. Okay, we're going to talk about all of our exponential functions here. The definition of an exponential function with a base A is denoted by. Why is this an exponential function? Because there's an exponent. That is what? A variable. When you have a variable in the exponent, which is right there, it's a variable. When you have a variable in the exponent, it's an exponential function. Does that make sense? Okay. What does it tell you about A? Greater than 0. Okay. It's not a negative number. And it's not just 1. So you'll have something like 3 to the x power. If you were to make a table of values, you would just plug in negative numbers, positive numbers for the x and see what you get. Right. That's an exponential function. And we'll talk about graphing them and all that stuff here in a second. If you're evaluating an exponential function, all you're doing is plugging in. So if I give you a question that says evaluate this function and round your answer, does anybody have a calculator? Francisco, you got one. Okay, you got one too. Let's check each other. If I have f of x equals 0.5 to the x power and they say to evaluate at 1.2, what you're doing is you're taking 0.5 and you're plugging in the exponent 1.2. So when you do that, 0.5 to the 1.2 power, what do y'all get?
0.435275.
Okay, round your answer to 3 decimal places.
0.435.
Do we agree?
Yes.
0.435, okay? If you have this, f of x equals 150, 2 to the x power, all you're doing is taking 150 and multiplying it by 2 to the negative 2.5. What your calculator is going to do, you have to put that in parentheses. Your calculator is going to take 2, raise it to the negative 2.5 power, then multiply it by 150. So what is that? Anybody? 26.516? 517. All right? You're just plugging in the calculator. That's it. We okay with that? Probably not a bunch of those. All right, this slide is very important. There's a lot going on, so I want you guys to see this. Characteristics of exponential functions in the form b to the x power. Look, I gave you a little example here. 3 to the x minus 4. What is something that's added or subtracted to the end of a function make it do? Shifts it where? If it's at the end, up and down, okay? These are what an exponential function looks like. If your b, the base, is greater than 1, it's going to be what we call a growth. It's going to go upwards. If it is a fraction, you see here how they say between 0 and 1, it's going to go downwards. But it's like a smooth curve. It starts off slow and then gets big in a hurry. So when you guys draw these, it needs to be a smooth curve looking thing. But what makes it either come from the top left to the bottom right or from the bottom left to the top right all has to do with the base, if it's a whole number versus a fraction. So if I look here, the domain is all real numbers. You can plug anything you want in for the x and the exponent. Anything you want. Okay? You can plug in negative numbers. You can plug in positive numbers. The range is all the positive real numbers for your parent function of this, b to the x. Anything you plug in, that's fine, but you're going to get a positive answer, is what they're saying. Your asymptote, what is the line that this blue line and the purple curve, what does it get really, 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 really close to but doesn't touch? The x-axis, okay? Your asymptote is going to depend upon your shifts up and down. What do you think the asymptote is here? What's the asymptote for 3x to the negative 4? 3 to the x minus 4, so I should say. Where does this smooth curve, where does it shift down to? Negative 4. So it's going to get really, 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 really close to the horizontal line, negative 4, but never do what? Touch it. If it was plus 5, that means it moves where? Up. How much? 5. There you go. Okay, good.
Wait, can you keep it on?
Oh, yeah, I'm not going anywhere. I'm still talking about it. What else? Just think about it. This makes sense. If I follow my blue line from the bottom left up, what is it doing the whole time? Going up. What is that? What do we say? Math ways. It's increasing. If it's coming from the top left and coming down, it's doing what? Decreasing. Good. So if you have a fraction as your base, your graph is going to decrease. If you have a whole number as your base, your graph is going to do what? Increase. Very good. Good, 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 good. The bigger the base, like 2 to the x, 3 to the x, 4 to the x, the bigger the base, the steeper your curve is. It's going to go, just get steeper as you go up. It's a one-to-one function. It does have an inverse. And again, your asymptotes, it's going to get really, 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 really close to, but not touch. Okay? So this is on the, you guys can see it. Now, if I have something like this, I'm just going to put something up here so we can talk about it. And we'll talk more about this in a second. But say I have 2 to the x plus 6. Where is this? First of all, is this an increase or a decrease? Is this going up? Is it sloping upwards or is it coming downwards?
Upward.
Up. Why?
It's positive and it's a whole number.
Not because it's positive, but because the base is a whole number, right? Where is this whole pretty curve? If it was just like this, 2 to the x, my asymptote, the horizontal asymptote, it would get really, really, really close to what axis? The x. It would get really, really close to the x-axis, but not touch it. Here, in this case, where does this graph move? Up 6. So it's going to get really, really, really close to the line y equals what? Horizontal line. Y. It's going to get really, really close to y equals 6, but not touch it. If I had something here, where do you think that moves it? Left and right. Good, because it's with what? With the x. Is it going to go left 3 or right 3?
Right.
How come? Opposite of what you think. Good. Okay, so in a case like this, when it says graph the exponential function, what I want you guys to do, and I will probably give you a table of values to look at, but if you are going to graph this, you literally are plugging in a table of values. You want left points that are on the left-hand side and the right. So if I did a table of values, I'm just going to do -2, -1, 0, 1, and 2. So think about this, guys. When I evaluate, if I evaluate 3 to the -2, does anybody remember what we do with negative exponents? Are we allowed to have negative exponents? Put it in a fraction. This is really 1 over 3 to the second. Well, what is 1 over 3 to the second? What's 3 squared, guys?
How do you know that it's...
How do I know what?
I'm going to do this.
Okay, how do I know what?
Like, why'd you put in the fraction?
Because it's a negative exponent. In order to make it positive, you have to put it...
Under?
So what's 3 squared?
9.
9. So I have a point at -2, 1/9. So now if I evaluate with -1, how do I rewrite that? 1 over 3 to the first, so it's really what? 1/3. Now I plug in 0. If I have 3 to the 0 power, what does that equal? Guys, anything to the 0 power? 1. Good. And then it's easy. Then I have 3 to the first power, which is what? 3. Then I have 3 to the second power, which is 9. So if I was going to graph this, I have a point at -2, 1/9. So we'll say, I don't know, it's there-ish. Doesn't have to be perfect. Then I have a point at 1 and 1/3. So it's a little higher. Then I have a point at 0, 1. Then I have a point at 1, 3. And then I have a point at 2, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So do you see how your function starts out slow and then it does what? It gets big in a hurry. We're going to hug. We're going to get real close to that x-axis, y equals 0, but don't touch it. What is my intercept? Where did it cross the y-axis?
Up 1.
At y equals 1. So if you had this function that said +2, you would just take your numbers, like when I plugged in -2, I got 1/9. It would be 1/9 plus 2. And then 1/3 plus 2. It just moves everything up. That's it.
What time is this class in? 10:15.
What time is it?
2.
Oh, great. We're not going to get through this. All right, so now, how is this function different?
It's a negative exponent.
negative exponent. So again, let's make an xy chart. xy, so I have -2, -1, 0, 1, and 2. So I have 3 to the -2, which is what?
1 over.
Well, what's a negative and a negative? Positive, so it's 3 to the, which is 9. So then I have 3 to the -1, which is the same as what? 3 to the 1. Then I have 3 to the -0, which is what? No. 1. Then I have 3 to the -1, 1/3. Then I have 3 to the -2, which is 1/9. So look what happens here. -2, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I have -1, 3. Then I have 0. Then I'm right here. And then here. What do you guys notice happen here?
It touches.
They're the same, it just what? Flipped. Good. Very good. It flipped over which axis? The Y. It went from the right-hand side to the left. Guys, did you already know that was going to do that right here? With our transformations? Yes. Because you have a negative with the X. So you would think it would flip over the X, but it really does what? Flips over the... Good. Very good. Okay. Same thing here. If I graph this, tell me what this should look like. This one versus this one. The fraction will look like what? It's going to decrease. And what does the whole number do? Increases. Good. Okay. Okay, we're going to talk quickly about this because this is the same thing we've talked about a million times. A vertical transformation. Look where the vertical transformations occur. Where? The constant. The plus or minus at the end. This is what we've talked about with every single function. Your plus or minus at the end is going to shift it which way? Up and down. Right? Look where this shift is. Where is that shift? Okay, it's left and right. That is with our exponents. If it's with the x in the exponent, we're going to go left and right. If it's at the end, we're going to go up and down. What about these? If I have a negative out in front, what happens? It reflects over what? The x or y? X. Very good. If I have a negative in the exponent, it reflects over what? Good. Same stuff we've done a million times. If we vertically stretch or vertically shrink, remember the vertical stretches are out in front. That's a vertical stretch or compression. Out in front. If I have something multiplied inside, what is that? That's going to be our horizontal stretch or compression, shrink, however you want to say it. Nothing new. Absolutely nothing new. Just the function has changed. The parent function has changed. But are all of the same things that occur transformation-wise all happen in the same kind of area? Does that make sense? You can see that? Okay. All right, so if I have something like this, and we'll talk about graphing more on Tuesday. Yeah, Tuesday. I just want to get through these notes. But how are these two functions different?
One of them goes, what's it called?
The first one?
One of them goes up 3.
Okay, this one shifts which way?
Left.
Which way?
Wait.
You just told me up
yeah.
3. Good. This right there tells me it shifts up 3. That's it. So where is the line that this is going to get really, really, really close to but not touch?
The
Y equals?
4.
Nope.
Wait, 3.
Y equals 3. This is going to be our asymptote at y equals 3. The asymptote here is at y equals 0. And we'll talk more about graphing. What about this one? Same thing, same concept. I have 4 to the x, and I have 4 to the x minus 2. But where is the x minus 2?
It goes right.
It's in the exponent, so it's going to go right. Good job. 2 spaces. Why does it go right? That's a minus sign. Opposite of what you think. The only thing that's changed here so far, guys, is just the function itself, that parent function. We're not talking about a cubic or quadratic or linear. We're talking now about an exponential. But your shifts Your stretches, your shrinks, your compressions, your reflections all occur in the same manner that the last one did. All right, if I talk about a one-to-one property, we'll talk about this a little bit more. But remember, anything raised to the 0 power is what? 1. You need to remember that. If you're going to solve using the one-to-one property, what you want to do is get the bases to be the same. So if I look at the base of 3 and the base of 9, can I rewrite 9 as good? You remember this. Can I rewrite 9 with a base of 3?
Yeah.
Yes. I have 3 to the x minus 2 equals, what's another way I can write 9?
3 squared.
3 squared. Once your bases are the same, anybody remember what we can do? You can cross them off. So then you solve. X minus 2 equals 2. So now what?
Add 2.
Add 2 to both sides. So x equals 4. The beauty about this is you can plug it in and solve. If I plug 4 in right here, what's 4 minus 2? 2. And what is 3 squared? Perfect. Does that make sense? We okay? All right, now let's look at this one. I have a fraction. So when we see a fraction, we should think negative exponents, always. I can rewrite 1/2 x as what? I can write it as 2 to the what? To the negative 1x, right? You don't have to write the 1 if you don't want to. I'm just showing you. But if if I bring this up, then my exponent becomes negative. So now think about the bases. I have 2 and I have 16. Can I rewrite 16 using a base of 2? What? 2 to the 4. So this is really 2 to the negative 1x. Again, you don't have to write the 1. I'm just showing you. Equals 2 to the 4th. Now that my bases are the same, what can I do? Cross them off. So negative x equals 4. So then what do I do?
X equals negative 4.
X equals negative 4. Divide by negative 1. Good. And x equals negative 4. Good. Good. All right. This is not a trick question. It just makes you think a little bit. I have a base of 6 and then a 1. Can I rewrite?
Yeah.
How?
You can 0.
What, Maria? If I make x 0, what is 6 to the 0 power?
1.
So x equals what?
1.
No.
Wait, sorry, what happened? 0.
X equals 0. Good. Very good. Good job, Maria. Good job, good job, good job. You guys are remembering this. All right, natural base of e. You guys have a button on your calculator that says e to the x. Okay, you have a button on your calculator that's pi, right? If you hit pi, it's 3.14, blah, 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 blah. If you hit e to the x, it's 2.718, blah, 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 blah. It's just an irrational number. So e to the x is our natural exponential function. It's just evaluating using that. This is where that came from. I'm sure all of you are going to go home and research this over the weekend on how the value of 1 plus 1 over n to the nth for increasingly large values, right? You guys are all going to do that this weekend? Okay, good. Let me know what you find out. All you're doing here is what? First of all, what does it say? Use a calculator. None of you can do this in your head. You don't know what the E is. So all you would do is in your calculator hit E, and then your x that you would plug in is 4.2. That's it. So if you have this bottom one, 125e to the 0.05 times 30. This is an exercise in do you know how to use your calculator? We will work on this more on Tuesday because some of us, we don't use calculators a lot. But your calculator, guys, is only as smart as your user. If some of you in here right now put negative 2 squared, your calculator will say negative 4. And you'll tell me, my calculator is broken. No, it's not. What do you have to put negative numbers in so they feel safe and happy? Parentheses. You have to give them a hug. So make sure you guys are using your parentheses. There's some calculators that I'm not super familiar with, so if you guys have questions about it, I will try and answer them. But again, if you're going to graph this, you're going to use a table of values. I would use always, if you could, 2 negatives, 0, and 2 positives. So if I had negative 2, negative 1, 0, 1, and 2, how would I evaluate this? In my calculator, I would say 4e, and then I would write negative 2 plus 2, and I'd get my answer here. Then I would say 4e to the negative 1 plus 2. Do you see what we're doing? You're just plugging in. That's it. And then you get your points and you graph it. Again, we'll do this more on Tuesday. But all this is just calculator work when you're using the E because it's an irrational number. Compound interest. You will have questions about compound interest. You have to know these formulas. Get this in your brain. Compound interest versus continuous compound interest. If something is continuous, you guys want a question like that. You remember our friend, his name is Apert. Right? When you see continuous compounding, you remember my friend, what's his name? Apert. P is the principal. It's what you start off with. E is that little button on your calculator. R is the interest rate, but you have to make it a decimal. And then T is the time. This formula up here, those letters still mean the same thing, but you have to remember P is your principal, what you start with. R is your rate. N, anybody know what N is?
Oh, no.
Oh, no. For N compounding per year, N could be, if I say something is compounded yearly, what does the word yearly mean? How many times a year? Once. If I say semi-annually, twice. If I say monthly, 12. If I say quarterly, 4. Okay, good. So you guys know what those words mean. You know what those words mean. So let's look at this. If I have compounded semi-annually, N equals what? 2. If I have quarterly, N equals what? 4. If I have monthly, N equals what? 12. And I see compounded continuously, so I remember my friend who is Apert. All right? Now, you guys are we'll do some interest formulas. I will finish this because I think the bell's going to ring. I'll finish this problem so you can see it. But in this example, write down the information they gave you. P is your principal. What did you start off with? What does it tell you started off with? $15,000. Okay? Agreed? That's your P. And then it says compounded for 2 years. That's my time. 2 years. And then I have an interest rate. What is my interest rate? What does it say? 3.2%. That is a percentage point. Is that a decimal equivalent? No. How do I make that a decimal? I'm going to move the decimal place over 2. Just because there's a decimal point in it doesn't mean it's already in decimal form. So your rate here would be 0.0, right? 32. And then you would use the formulas. And again, I'll do this before I upload the video. But you'll use the different formulas to find the answers. Semi-annually, quarterly, monthly, all of your answers should be different because you're using the formula. Sound good? All right. Have a good weekend, guys. Okay, so I'm going to finish up this last slide on the video so you guys can see. I am looking here. Hold on, let me move this for a second. All right, I'm looking here at this problem. It says find the accumulated value of investment of $15,000 for 2 years at an interest rate of 3.2% if the money is. Okay, you have to know what these words mean, guys. Semi-annually. How many times a year is semi-annually? 2. So in this case, you would plug in 2 for your N. How many times a year is something compounded quarterly? 4. Think about how many quarters are in a dollar. 4. How many quarters are in a football game? 4, okay? If I talk about something being compounded monthly, how many months are in a year? 12. So we need to make sure we understand that. And then when I have compounded continuously, I think of my friend and his name is? Apert. Good. So another thing to bring to your attention, if I were you, I would write out your variables. P is the initial amount invested, that's our $15,000. T is our time in year, so it's 2 years. And R is our interest rate. Guys, it has to be written as a decimal. I understand that 3.2 is a decimal, but it's got a percentage sign behind it. It's 3.2%. So in order to use the rate in the formula, what do you have to do with that decimal point? You got to move it over 2 places. That's where I got the 0.032. Does everybody understand that? So let's work these problems out together. If you have your calculator, I'd really appreciate you chiming in as we go through. Look, I have my formula right here so we can look at it. But if I have something and I'm compounding it semi-annually, my N, in this case for letter A, N equals how much? Semi-annually? 2. So I'm going to take my formula. And I have my principal, which is 15,000, correct? Times 1 plus, what's the interest rate? 0.032 divided by, what is our n? 2. And then that's raised to the n times t. So n is what? 2. And our t is what? 2. Now what you guys are going to have to do is input this in your calculator correctly. You should do it exactly like you see it. Type in 15000 parenthesis 1 plus, hit the fraction button, 0.032 over 2, close your parenthesis, and then the caret button, looks like top of an arrowhead. You want to raise that to the, what's 2 times 2? Fourth power. So if I am compounding something semi-annually, twice a year, tell me what you got in your calculator. We're talking about money. Don't tell me 15,000, 0.736549. 2 decimal places. Talk about money. What is it?
$15,983.28.
$15,983 and what? 28 cents.
You can round it.
Okay, so I agree. We're good there. All right, so now we're going to do the second one. Again, guys, this is on the teacher copy. It's uploaded. Let's look at B. We'll work on our calculator entering in a little bit. I have the same principal of 15,000, correct? I still have 1 plus. The interest rate is still the same, 0.032. But this time, how are we compounding? Quarterly. So my n becomes what number? 4. And then I raise that to the 2 times 4 power, which is really 8. Yes, you can just put it as the 8. So what do you guys get? 15,000 times 1 plus 0.032 divided by 4 raised to the 8 power. What do we get? Read it to me. 15,000?
15,987.3.
So 30 cents?
31. Yes.
Oh, 31? Okay, good. Did you do that on your iPad?
Yes.
How cool.
It's a better calculation. Now.
Hold on, I'll look at it in a second. I'll look at it in a second. All right, C. Again, we have the same principal that we invested. 15,000, 1 plus. The interest rate is still the same, 0.032. But this time it's compounded how? Monthly. So my number underneath my denominator should be 12. So then I raise that to the, God bless you, 12 times 2, right? Because it's 2 years. So it's the same as to the 24th power. So what'd you guys get? Read it to me again. It's 15,990. How much?
2 cents.
And 2 cents. Good.
I got it.
Point what?
Yeah.
Okay, perfect. And then the last one is compounded continuously. When I think of compounded continuously, I think of my friend, and his name is A. Pertz. So you are really going to go 15,000, then hit the E button and raise that to the R times T. What is my R? 0.032 times, what's my T? 2 years. You guys have to know these two formulas. You have to. Okay, so you got for continuously $15,991 and how many cents? Sean?
15,991
38?
and 39 cents.
39 cents, something like that? Okay, good. Guys, remember, we talk about money, it's 2 decimal places. Somebody asked me last period, why do you put the 39 tiny? I don't know. It's just the change. That's all I'm saying. It's not like, you don't have to write it like that. But what do you notice about these numbers?
They go in like increments.
Is it a huge difference? No. So make sure you guys are paying attention to that when you're doing these. All right, so I'm going to upload this video.